In this video, we're going to go over two more types of organic reactions, which are substitution reactions and esterification reactions. So in this first type, substitution reactions, essentially what we're doing is we're replacing one atom with a different atom. Okay, so what you're going to be looking for if you're looking at a reaction and trying to identify what type it is, for substitution reactions, you're going to have two compounds reacting to form two different compounds, but carbon atoms are bonded to the same number of atoms as in the reactants. Okay, so essentially if we look at this template here, okay, essentially two atoms are just doing a monkey switch essentially. Okay, so originally the carbon atom is bonded to atom Y here, and effectively atom Y does a little monkey switch with atom Z, and atom Z attaches to our original carbon atom that Y was attached to. Okay, so that's the basics of this. Okay, so typically alcohols undergo substitution with an acid containing a halogen. So for our first example, we've got ethanol. So that's an alcohol with two carbons in it. 1, 2. Here's our alcohol group, and that's reacting with hydrogen chloride. Okay. So I'm just color coding this so that it's easy to track where everything's going. Okay. So with this, effectively what's going to happen is our alcohol group is going to substitute or make a switch with the chloride. So if I draw this out, we will get this, and our other product will be water. So without getting into too many details, because if I did that would go way beyond the scope of Chem 30, but how you know that it's hydroxide and chloride that switch is because hydroxide, when it's by itself, typically likes to have a negative charge. Okay, and chloride, when it's by itself, also likes to have a negative charge. So you could kind of think of it as the functional group that likes to have a negative charge is going to switch with the other thing that likes to form a negative charge as well. So if you're wondering, well, why are we switching the hydroxide or the alcohol group with the chloride, that would be the reason why, or that would be how you know what to switch with. Okay. Next, alkyl halides undergo a substitution reaction with a hydroxide ion. So in our second example, we have chloroethane reacts with a hydroxide ion. So chloroethane, that means we have two carbons in our parent chain, which only has single bonds. There's a chlorine in there. Okay, so 1, 2, here's our chlorine, plus, and then hydroxide ion. That's just like that. So you could write it like this or like this. It's the same thing. Okay, I like writing the negative beside the oxygen just because that is actually where the negative charge does sit. It doesn't sit on the hydrogen. Okay, so what we're going to get for our products, if we remember, you know, negative is going to switch with negative, so the chlorine is going to switch with the hydroxide. We will get this. I'll draw that a little closer. And then we're going to end with chloride ion. All right, so with these types of reactions, one thing to kind of help yourself out is you could think that if you start with a negative charge, you should end with 1 negative charge. Okay, so that's kind of a way that you can like check that you're doing things right. So let's just write that out. So aromatic hydrocarbons will undergo substitution with chlorine and bromine. Aromatics are very stable, so what that means is they're very unreactive, okay? And so they're only going to react in the presence of a catalyst. So what that means is because compounds like benzene, which is an aromatic compound, because it's so stable, it really doesn't like reacting with other substances. So the catalyst is basically there to help the reaction along. So for example, we have benzene, which reacts with bromine in the presence of a catalyst. Okay, so I'm going to draw out benzene here. So remember, benzene has those alternating double bonds, and we're reacting it with bromine. With some catalyst, but we're not given the identity of the catalyst. So I'm just going to write that over the reaction arrow. Okay, so what I'm going to do is I'm just going to highlight the specific hydrogen. Now, what I'm trying to say is one of the bromines will do a monkey switch with this hydrogen. Now, does it have to be this hydrogen in particular? No, it could have been this hydrogen, or the hydrogen on this carbon, or this carbon, or this carbon, or this carbon, right? Like, in the end, so long as you're monkey switching one hydrogen on the benzene with one of the bromines, you're good. Okay, so I'm just going to draw out the monkey switch right here, so it's a little bit easier to predict what the products will be.
So I'm like, didn't do all my pleasantries.
Okay, so that's one of our products, and then for the other one, right, so since this hydrogen switched place with this bromine, that means our other product is going to be hydrogen bromide, or in other words, hydrobromic acid. So alkanes are also pretty stable, so they also don't like reacting with other substances, and they will undergo substitution with chlorine or bromine, but only in the presence of UV light. So basically the UV light gives the alkane like enough energy to want to react with something, some other substance, such as chlorine or bromine. Okay, so here we have an example where we're having methane reacting with chlorine, and then UV light helps this reaction along to give us chloromethane, dichloromethane, trichloromethane, tetrachloromethane, as well as hydrogen chloride. Okay, so what you need to get out of this is that alkanes can undergo substitution with either chlorine or bromine, but it needs UV light. That's what you need to get out of this. Because this is a bit more of a complicated substitution reaction, you're not expected to know or be able to predict the products for this type of reaction. However, for simple substitution reactions, absolutely, you need to be able to predict those products. All right, moving on to esterification. So esterification is all about reacting a carboxylic acid with an alcohol to create ester and water. Okay, so this is our general template that we're going to be following. Okay, and in order to form an ester, what needs to happen is essentially we need to cut water out of the carboxylic acid and the alcohol. So we're grabbing the OH from the carboxylic acid and the hydrogen from the alcohol. So you're always going to be taking the OH from the carboxylic acid, and you're always going to be taking the hydrogen from the alcohol. Okay, so we're removing water because it's H2, there's 2 hydrogens and an oxygen. Remove water to form a bond. Okay, so what bond are we forming? Well, we're forming this bond right here. Okay, so just with like how we talked about naming esters, okay, this is why I was saying, okay, part of it comes from a carboxylic acid. So this part comes from the carboxylic acid, the one with the carbon double bonded to the oxygen. Okay, and then the other half of the ester comes from the alcohol. Now, just as a reminder, R and R prime are just talking about 2 different carbon chains. Okay. Something that's kind of tricky about esterification reactions is students usually forget to write water as a product, so don't forget about that. Okay. So esterification is one type of condensation reaction. Okay, so you do need to know that it is a condensation reaction. How do we know that it is a condensation reaction? Because any reaction where we can produce water would be qualified as a condensation reaction. So condensation reaction, that just tells you that water is a product. Okay, and in general, a condensation reaction is a reaction in which 2 molecules combine to form a larger molecule and another small stable molecule, which is often water. Okay, so for the purposes of Chem 30, you can assume it's always going to be water. All right, so example 1, we have benzoic acid. So because it ends in oic acid, that's how you know that's your carboxylic acid. Reacts with ethanol. So that OL ending tells you that it is an alcohol. So let's write out benzoic acid. So that's going to be benzene with a carboxylic acid functional group. So just a reminder that there's multiple ways to represent benzene. So I could do the alternating double bonds, but keep in mind benzene can also be represented, like all those double bonds can be represented with a circle in the middle too. Okay, so just watch out for that. Be able to identify, you know, all the different representations of benzene. Okay, and then just to make my life easier, for the alcohol, I'm going to write it like this. Okay, so as a reminder, our goal is to cut out water to produce a bond. So I like putting a square around water just to kind of help my eyes here. Oh, I better put in that plus sign. Okay, just to mean like these 2 molecules or these 2 compounds are reacting with each other. Okay, so I'm going to write water as a product just to get it out of the way so I don't forget. Plus, all right, so what is our ester going to look like? So I'm going to draw in the benzene. Okay, all right, now this is the tricky part. So this carbon bonds with this oxygen. Okay, so I'm going to start off. Okay, so there's my carbon double bonded to oxygen. Now we need to single bond it to oxygen. Okay, so this oxygen right here is that oxygen. Okay, now at this point I just find it's helpful just to count how many carbons that you have in your alcohol. So 1, 2. So I need to put 2 carbons after this oxygen. 1, 2. There we go. All right. So moving on to our next example here, we have propanoic acid reacts with pentanol. So let's get started here. So propanoic acid means prop, we have 3 carbons. 1, 2, 3. But it's a carboxylic acid here. So then it's going to look like this. Okay, and then our alcohol is pentanol, so there's 5 carbons. So 1, 2, 3, 4, 5. Okay, we're chopping out water, making sure to take the OH from the carboxylic acid side. Nope, I should have drawn this smaller. Let's see if I can narrow this down. There we go. Okay, so oftentimes where students will make mistakes is like putting in enough carbons into their ester. Okay, so again, let's count. 1, 2, 3. There's 3 carbons there. So 1, 2, 3. Okay, so this carbon right here is that carbon right there. So we got to represent that it's double bonded to that oxygen. Okay. And then we have to make sure that we're saying this carbon, it forms a bond with this oxygen. Okay. And then there's 5 carbons that are attached to that oxygen. So I'm going to make sure to count them out. So 1, 2, 3, 4, 5. And before we finish this, let's make sure we add in water here. There we go. Okay, so we got our ester and our water, and again, make sure you don't forget about water. It's the most commonly forgotten about thing in esterification reactions.